We did the phase-based basic calculation. Again, little bit of antennas will move on again. Right? So propagation little part we temporarily hold, and then move on to antenna. Here we try to understand two types of antennas, two different categories of antennas. So submitting you can write two categories of antennas. Two categories of antennas. This is again little out of syllabus, but a little shortcut for you to become more confident about the antenna. Okay. We divide the antennas into two main categories. One category we call line type. This is not a theoretical category, something we define. There is one type called line type, another one called aperture type. For example, a dipole, when you take, it has no area actually. It's just a length that you use for the calculation. Lambda by 4, lambda by 2, lambda by 8, 5 lambda by 8, like that. You have various lengths defined for line type antenna. But for the microwave dishes that you have seen in the tower, it is not the length, it is the area. They are called aperture type antenna. Aperture type antenna. You also have two. What are the aperture type antennas you have? You are looking at me using those antennas. You have two of them, and it is the area. Why is the eye like this? Why don't they make an eye like a saucer? Big one. You could have seen along the distance. That's it. Did you ever think, why am I having small antenna? Small aperture. Small aperture. Not a big aperture. If you have a big eye like this, two of them, maybe a little ugly, but it will be very powerful. You can see up to Boral. And you can see two ants walking down. At the moment you can't. And so this is the situation now. And then you can realize why the optical band was selected. Why do we select optical frequencies? Because lambda is short. So lambda is short, a small length can make a big effective aperture. So that's why you are made to see optical. Instead they could have, whoever designed it could have made an antenna, some eye to see radio frequency. So you can see the waves going this way, that way. Luckily they didn't do this. They made a set of antennas which can see light, because the light came from distant stars and it illuminates the world, and at the same time it is small enough, because wavelength is small, the antenna is also small enough to be fitted to our face. Think wide like that. Why? Then you can understand antenna. Don't search for outside. If you want to study antennas, you have two here, two there. Okay? So study them first. Then you can see how they pick up. Now these things are directional, isn't it? These antennas are directional. Eyes are also directional. You have to turn this way. Otherwise it's not very wide angle. So all antenna properties you can learn from them. Also when you study light bulbs, like tube lights, etc., again you can study lots about antennas by looking at them. So please take such practical examples when you study, rather than linking up with lot of theory, because antenna is actually linked up with lot of theory, electromagnetic. But there is a way to simplify. One, what I am presenting is some little way to simply think about it. So there are two categories: line type, aperture type. Line type collects the voltage from the electric field in the sky. Aperture type collects power from the power density in the sky. That is why in our last example we calculated electric field as well as power density, because depending on the receiving antenna, one or the other is becoming important. So you can mention, we can broadly divide the antennas into two categories. Broadly divide the antennas into two categories. Number one, line type antenna. Number two, aperture type antenna. Line type antenna and aperture type antenna. Examples we will write. Examples, line type. Can you write the antennas you know which are something like line rather than an area? Make a try. What are the examples? You can easily say monopole. Monopole, what is the length? Lambda divided by? Lambda by 4. Monopole. Second one is dipole, lambda by 2. Dipole is lambda by 2. Rod antenna. Rod antenna. You have lambda by 8 going up to 5 lambda by 8. Variation, lot of them. All are called rod antenna. Some people call them Marconi antenna because Marconi is the one who invented Marconi antenna. Then in the diploma we studied the inverted L antenna, T antenna. Those are examples. All are like that. Inverted L antenna. Inverted L is capital L. In fact, the antenna was like this, isn't it? Like this. So we call it inverted L antenna. Then T antenna, because it was like letter T. T antenna. What else? Rhombic antenna. But maybe we should avoid saying rhombic, because rhombic is not an antenna, it is an antenna array. It's not one antenna, it is several antennas working together. So let us put that separate. So rhombic don't write. Wire antenna you can make. Single wire antenna. So those are few examples. Then aperture type. Second category, aperture type example. Aperture type, you can write few examples. The best example could be the microwave dish, which is called the parabolic dish antenna. That you see everywhere, parabolic dish antenna. There is another type very popular known as horn antenna. Horn, H-O-R-N, horn antenna. When you see a satellite dish, normally it is focused to a horn at the focal point. Horn antenna. Then there is another type called fast horn. Another one called hog horn antenna. These are large ones. Hog horn. Why don't you mention your own eyes? So they are also antenna. Just say, my eyes. Aperture type antenna. Then lens antenna. Lens antenna. Our eye has been imitated in the lens antenna like this. You make a lens and focus the energy into a focal point. Lens antenna. Okay, that may be enough. So those are examples for aperture.
So loop
And then
antenna.
another antenna called cosec squared theta. Yes, loop antenna also cosec squared theta antenna, which is a radar antenna. You would have seen this kind of radar antennas which are rotating like this. They are called cosec squared theta antenna. They are not parabolic. They are partly parabolic, partly hyperbolic. Cosec squared. Then there is loop antenna, which is also area. Loop antenna. Okay. So this is to get some understanding of the antenna. We divide them into two. Then maybe we can differentiate between them like a table. If you have a small table. On this side we will say line type. On this side we will say aperture type. Aperture means area. What are the differences in operation? This is light type antenna collect energy from one field, either electric or magnetic. Collect the energy from one type of field. From one type of field. Example, E field, electric field. Aperture type, you can collect the power using an aperture. Collect the power using an aperture. Because there is a power density inside, you can collect the power from there. That may be first point. Second point we will say, let us say L is the length. Here we use physical. Is the physical length of the antenna. Instead of that, on this side you have A physical, which is called the physical aperture of the antenna. What is the difference? This is in meter. This is in meter square. This is an area. This is the length. There is a physical length on this side, there is a physical aperture on the other side. And there is another notation called LE, called effective, electrically effective. This side LE, E for electrical effective. Electrically effective length of the antenna. So what should I write on the right hand side? AE, electrically effective aperture of the antenna. What is effective aperture? That means the aperture which is actually effective for collecting power. Then there is antenna efficiency defined. Antenna efficiency. In both it is antenna efficiency. You can guess electrically effective length is lower than the physical length. So therefore they define an efficiency for the antenna. It is electrically effective length divided by physical length. And you can multiply this by 100 and give it as a percentage if you want. And it has no unit. Meters over meters. Similarly, antenna efficiency in aperture type is electrically effective aperture divided by physical aperture. Still no unit. If you like, you can multiply by 100 and give it as a percentage. This is called aperture efficiency. This is called length efficiency. Slightly different in words. Length efficiency, aperture efficiency. But both are same efficiency of the antenna. What do you think is the typical efficiency of an antenna? What percentage of physical aperture is electrically effective? So what percentage of physical length will be electrically effective? That again? Will it be very high efficiency or very low efficiency in antenna? Can I have an efficiency like 95? We must have a sense to the efficiency. We can't get, right? We can't get that. Most factory antennas have around 60-65. Other areas are wasted. So we just mentioned it is approximately about 65%. Here also about 65%. Correct. Mention approximately, it can vary. Then equation wise we use, if I want the terminal voltage, I can find out the electric field intensity at the receiver. Now you know how to find electric field intensity at a length. At the point where you install this antenna, you can calculate the electric field intensity created by the transmitter. And what does that mean? It is volts per meter. Volts per meter. To find out how many volts, what should I do? From volts per meter to volts, multiply by meter. Multiply by the electrically effective length. This is volts per meter, multiply by the electrically effective length, volts per meter into meter, will give you what is the terminal voltage across the dipole or across the antenna. So this is how we calculate the voltage induced in the receiving antenna. You already know how to do this. Before the break we discussed. If you know the electrical effective length of the antenna, you can find what is the voltage in the terminal. For example, if you want to find what is the voltage in the home dipole for TV receptor, you can do that. In the aperture type, you can't calculate the voltages like that. You calculate the power received. How do you find? Power received. You already know the power density. What is the unit? Volts per meter square. And then you find how many meters square are we using to collect the power. Multiply. Then you get what? Multiply by meter. For example, in this room, you have a certain illumination level falling on your paper. Certain watts per meter squared is falling on the paper. And If you multiply that by the aperture area of your eye, what is falling onto the eye and the aperture area, you find how much of energy is falling onto the retina behind the eye. And that is the one which is being converted to the neural signals and being transferred to the head, isn't it? Okay. So the sensitivity of the retina has been made to handle that power, but you know what happens when I put a torch to your eye, isn't it? What is happening? Suppose I put a torch to his eye, he will immediately close, right? Otherwise the retina will burn, because retina is not made to handle that kind of a power. That's why they advise you don't look at the sun directly, don't look at the welding. Why? Because the power density is too high, and the power collected by this aperture will be too strong for the retina to survive. Likewise, compare with yourself and study. Okay, so this is how to calculate the receiver voltage. This is how to calculate receiver current. Can you see the difference now? Well, these things we don't write for the exam, right? This is for our own understanding only, and you might not find it in textbooks also. Just with experience that you can compare things like that. But remember, this has a shortcut to remember, shortcut to visualize things. Okay, close the table. Close the table. Now we'll go back to our early example. Please say. Something I forgot. Now you close the table, isn't it? Hope you can find little time to squeeze something. It is on the aperture side. Gain of an antenna is I forgot that. Right? If you know the effective aperture, you just multiply that by 4 pi lambda squared, you get the gain of the antenna. That is only in the aperture side. In the line side, there is no equation like that, no equivalent line. So once the aperture is known, multiply it by 4 pi lambda squared, you get the gain. The gain can be calculated there. We'll do an exercise from line type antenna. So we can say exercise line type antenna. Later on we will do aperture type. And I want you to do that. So this is completely yours, but I am combining this with something you already calculated. Earlier, you fed 100 watts to this, isn't it? Gain was 1.64. And you took 100 meter length, and you found the electric field strength here. Let us call it ED, electric field due to the direct wave. The direct wave term. You already did that. Now let us extend this little bit. Now that you know there are line type and receiving type, let me put another receiving antenna here, another dipole. Physical length is lambda by 2. Always remember, in a dipole, electrical effective length, this is coming from electromagnetic, is not lambda by 2, it is lambda by 5. Lambda by 5. So please remember this. Electrical effective length is lambda by 5, not lambda by 2. Lambda by 5 is smaller than lambda by 2, you know that. So electrically all that length is not effective. It's less length is effective. Right? So can you find out how much of voltage will come there? What is the received voltage in this antenna? So we just extend that example. So think of the theory now and apply it. And use the early answer because you already have the electric field. What is the field strength you calculate? You told me it's about 1.3 microvolts per meter. Millivolts. Let's call it D for direct wave. 0.7. So ED was 0.7 volts per meter. Assume that I am operating this signal on assume it's a 900 megahertz cellular signal. So take lambda like 10 meters. Frequency is 900 megahertz. Assume I am transmitting at 900 megahertz, which is your cellular band. Cellular band. So I want you to find out VR using that earlier table. You know the electric field means what is the potential difference per unit length. What is the potential difference per unit length? And there is this much of length now, this much of length. So then what will be the potential? Potential difference per unit length multiplied by the length. And automatically you get the potential difference unit length. We'll go for the answer and compare. What is the lambda in this band? Lambda is frequency is 900. So apply V equals F lambda, you can find lambda. How many meters?
0.33.
0.33 meters. Right? Is that it? So you get 0.33 meters or 1/3 of a meter. Here you get lambda when you calculate that 1/3 of a meter. From your basic knowledge, V equals F line. Then electrical effective length is 1/3 of a meter divided by 5. That means 1/35 meters. This is 1/3. This is 5, so 1/3. So just multiply these two. Simple. Field strength multiplied by the effective length, you get the voltage. So multiply 0.7 by 1/35. Find the answer, that will be in volts. So voltage is E into L is electric field strength into effective length.
0.07 42.
0742 watts. And it is 74.2 millivolts. Usually these antennas will pick up either millivolts or microvolts. 74.2 millivolts. So now you can see how that idea could be used in a practical situation. I am assuming only the direct wave. Why? because it is a free space. There is nothing to reflect. So only the direct wave will go. Right? Free space. That's why we got the direct wave. So put a sign mention. If the electric field intensity is multiplied by the effective length of a line type antenna, multiplied by the effective length of a line type antenna, we get the received terminal voltage. We get the received terminal voltage. That means voltage between the two terminals. So it's so simple like that. And you will find it similar if it is aperture type. Let us do it that way now. Just replace this example by an example 2 now. This time example is aperture type. So I will assume a microwave dish here. Assume a dish like that. Assume that I am radiating at say 2 gigahertz. 3 gigahertz, it is easier to calculate. And my gain is 3 gigahertz will get something like 20 dB is about 700. Take 100 meter away. Put another dish here. And collect the power. This time what I need is not the field strength, we need the power density here. And can you find the lambda here?
0.1 meter.
Okay, 0.1 meter. And that is 0.1 meter. What is the power density? Power density was D Ct over 4 pi times R square. So you can simplify that. Gain is 100. Ct is also 100. Divided by, sorry, I could not give it. Just assume I paid 100 watts, right? 4 pi times 100 square. Find out how many watts per meter square or milliwatts per meter square, whatever. It's 1/4 pi.
0.0795.
Okay, 0.0795 watts per meter square. Is it milli or what? What? So in milli it is 79.5 milliwatts per meter square. So that many milliwatts will go through 1 meter squared area. That many milliwatts will go through 1 meter squared area. Then what is the power that will be actually collected by this area? How do we find the electrical effective area? Assume that this also has a gain of 100, right? Same type of antenna. Gain is 100. Earlier I gave the relationship between, your table has relationship between effective aperture and gain. If you know the gain, it is effective aperture. How do you find? Look at the table. We are practicing the table actually. What should I do? Gain multiplied by lambda squared over 4 pi. D lambda squared over 4 pi. So shall we find that? According to the table, effective aperture is gain into lambda squared over 4 pi. Gain is known, lambda is known, so quickly find it. How many meters squared is effective aperture? Later on in satellite communication, we'll be using these calculators. So we are practicing for those applications. Okay? Comes 0.07. Okay, same answer. Okay, 79.5 meters square, is it? Answer could be anything else. Maybe the way I gave you these hundreds, it came to the same answer. 79.5 meters square. Ah, that's it. 0.79. 0.95 meters. Then how do we find, according to your table, if you know the power density? Power density means how many watts per meter square. And if you know how many meters squared is being used to collect power, just multiply the two. Watts per meter square multiplied by meter square should give us what? So just multiply this. According to your table, power received in the aperture type antenna is power density multiplied by the effective area. Power received by your eye is again the power density created due to the light multiplied by the effective aperture of your eye. If the power density becomes high, that's what I mentioned earlier, the eye may be damaged. So what is the received power? So 79.5 milliwatts per meter square multiplied by 0.0795 meters square. So then answer will be milliwatt. 6.3. 6.3. Did you get 6.3 milliwatts? Okay. So this much of power will be received at 100 meters using the similar type of antenna, but again I am assuming free space, direct wave only. So now can you see the difference in the way people do calculations in the line type and aperture type? Depending on the situation, you will have to adjust your calculation method. Okay? That's why we categorize it into two. So you can write. On the new line you can write. Note that there is a slight difference. In the way we calculate the received signal. We calculate the received signal depending on our use of antenna. Depending on our use of antenna. So for line type antenna, we may go by the voltage and electric field. We may go by the voltages and electric field. For aperture type antenna, we go by the power and power density. New paragraph. Consider a typical parabolic disc. Of diameter simple d. We call it mouth diameter. Mouth diameter, we'll say capital D. Okay. You have seen the parabolic disc like this. This is the reflector, not the whole antenna. It is a parabolic reflector. Mouth diameter means this length. This length we call the depth. Simple D. Simple D is the depth of the antenna. Capital D is the mouth diameter. circle. And you look at it from the front, the mouth is a circle, right? Diameter d. This front view of a parabolic disc. What is the physical aperture here? How much of area is physically seen? It's a circle. Aperture means what you see from the front. For the wave to come, how much of area? Pi r square, isn't it? Pi r square for a circle. It is pi times r is d by 2 square. So it will be pi d squared over 4. So physically it is a circle, pi r square. And we know that all this circle is not effective. Only about 65% of that is effective to collect the energy. Right? However, all the physical aperture is not electrically effective. Is not electrically effective to collect energy. Therefore, we already said earlier, effective aperture divided by physical aperture is efficiency. Therefore, effective aperture is efficiency times physical aperture. Effective aperture is efficiency times physical aperture. Theta is the notation we use for aperture efficiency. Aperture efficiency. Power efficiency of the antenna we will discuss later. It is aperture efficiency. Different types of efficiencies are there in that. So then it is efficiency time pi d squared over efficiency times pi d squared over 4. All are little simple equations, not big ones. It's the area of a circle and things like that. Right? But from your table, from the earlier table I gave you for the aperture antenna, can you find out the equation for the gain? How do we find the gain? Quickly refer that. Please refer that. What is the gain equation?
V equals 4 pi divided by lambda.
4 pi over lambda square multiplied by this term, isn't it? So shall we apply that? Because I have found AE. So if you know AE, you can find the gain from that formula. So you can mention from the table. From the table we said gain is 4 pi over lambda squared into AE. That we are not going to prove because that means electromagnetic knowledge. And we skip that. So electromagnetic is not in our syllabus. So we skip that. And we don't need it for most of the practical calculations. But to understand exactly how it works, you might need it. If you are doing a degree course later, you might be required to study electromagnetic. But to do a job, you can skip the difficult one. For example, now he's doing a job, isn't he? Does he know the chemical composition of cement? Do we know actually? Not him even. He might also not know it. We know that it is some aluminium silicate or something, some big one, but he doesn't need to know anything about it. But he gets paid for the job. You are also like that. You can be like that. Right? While doing the job, we can learn. Right? While getting paid for the amount, we can do. Right? So same way, a telecom engineer might not know everything. Right? So the beauty of going through a career is you can learn when you need to. You don't need to finish learning to start doing something. Some people wait until they finish everything to start a career. And they keep waiting. Long wait. It will be long wait, sometimes lifelong one. Don't do that. Just get involved with doing something, and while doing you can just think about the background. And when you start thinking about the background, there are a lot of knowledge coming. Right? Like for him, he can study about civil engineering or cement or materials, so many. For us, we can study electromagnetics, lots of these generic things, mathematical things. Right? But you can postpone them if you want to, until you really need to strike them. So build your career like that. Get the essential ones first. Start doing something. And after that, stop up and fill the vacancies. Okay? So, City and Guilds want you to adopt that approach. City and Guilds is a vocational qualification course. It is training you for a vocation, and they don't want to touch on the electromagnet. Just get the job done, install the antenna, make it working. Later on, if you really want to, if you become very puzzled about it, start learning electromagnet. Then you can learn about how did this equation come. E lambda squared over 4 pi, how did that come? That comes from a theory called solid dynamics, and we are not touching it. Right? So don't worry about it at the moment. Right? Okay. So coming back to this, what is the final answer when you get there? 4 pi AE divided by lambda squared is gain. So can you find the gain from that one? AE I have given. Maybe 2 steps or 3 steps something. I'm trying to find the gain of this. So this AE, take that and substitute. Efficiency time, efficiency multiplied by phi d over lambda whole thing square. This is good. That is one you should get. Final answer should be, I write the final answer, efficiency multiplied by phi d over lambda whole thing square. And we said that this efficiency is about 0.6, 0.7, something like that. So keep that also in mind. Note that antenna efficiency is around 0.65 or 0.7. Around 0.65 or 0.7 for most practical antenna. 0.65 or 0.7 for most practical antenna. So therefore, the manufacturer will then measure and decide what is the efficiency. So this is a good equation. If you remember to substitute 0.65 or 0.7 there, you can approximately get the gain of the dish. But what is important for us to note is that there is this d over lambda ratio. That means if mouth diameter is very large compared to the wavelength, you get very high gain. Mouth diameter is very large compared to the wavelength, you get very high gain. Now you can figure out why is your eye is small. Why is that? Why is it so small? It still has a high gain. Why? Because lambda is small. Right? Because lambda is small. So the diameter may be only 1 centimeter. But lambda is so small, it's 0.4 to 0.7, some micrometer. That is the visible wavelength you see. Say 0.5 micrometer. Then you can see 1 centimeter divided by 0.5 micrometer, whole thing square. Very high gain in your eye. Very high gain in your eye. So there is no necessity to make it a big one. Because we are supposed to see that set of wavelength which is varying from 400 micrometer to 0.4 micrometer to 0.7 micrometer. That is a visible optical wavelength size. So likewise you can even apply this to study your eye also, but don't damage it while trying to study it. Have you noticed that these things, if you have practically seen them, some of them are like this. The edge is like this. Bent this way. Did you know? There is a bent edge. So next time, please study. Every time you get this. Some of them have sharp edge, some have a bent edge. Bent edge. Why is the bent? It is good to hold because two people can carry it like that. No, because it does not affect anyway. Even the bending will give you additional strength to the disc because the rim is very strong. But anyway, that final area is not being used because it's not the effective area. Effective area is less than the physical area, isn't it? So whatever you do with the edge is nothing to do with the mechanical, electrical behavior. Therefore, you can use that to get mechanical strength by bending it. So people do various manufacturing inventions like that once they understand this theory. Once they understand that theory. So also you can cover part of your eye and see because it's not very effective. But don't cover the center. The major area is the most effective area to collect energy, but the outer edges are diffracting the energy a little bit, so it is not focusing sharp enough and therefore may not be electrically effective. For example, my eyes are not electrically effective at all. Today I forgot my glasses also. Therefore I barely see you, but may not recognize you even. So that happens to you also when you get age. So these antennas are going to distort it. The focal point will not be correct. So you might need external glasses to get the focal point set again. So just apply the analysis to yourself and experiment like this, experiment in thinking, and then you can improve your understanding on this thing. Okay? But the key here is thinking a little bit wide, okay? Out of the book. Thinking out of what is there in the book. That is the key for an engineer. You can never become an engineer if you stick to the book. Have you noticed that? You might have seen in your job engineers who are performing very well. Are they going by the book all the time? No. Most of the time, no. Good engineers are using the book as a tool only. But the rest of it is here, thinking out of the box and inventing for the solution there. So all the theories we discuss in the class are only as a support. Right? Only as a support. Don't believe 100% on this. Right? And it is not engineering what we write on the book. Engineering is not on the book at all. It is in practice. It's a practice. It's not a science, it is a technology. It is not something you study for reasoning, it is something you study to make solutions. So understand those differences and adjust your thinking, and then you can be a very good engineer. It may be good news to know that engineers don't need to study hard. We need to practice that. Maybe good news. Maybe there is an opportunity for every one of us there to practice that profession. But some of you think, okay, if I want to become an engineer, I have to go to a university to complete my degree and start. Wrong. Right? Completely wrong. From the university you get a little certification that you have gone through engineering degree. But you are not an engineer. An engineer is made by the practice he does. By the things he does. And so long as you are capable of doing things, you can do it. Right? You can do it. Right? So please adjust your thinking accordingly, because the wrong thinking can lead you in the wrong direction. And maybe you might try to continuously go after knowledge and finish and wait until you finish everything you know about engineering before you practice. We don't need to. Right now, maybe tomorrow, you can start practicing engineering. But the thing is that many governments in the world don't allow you to practice it for only others. You can experiment in your garage, okay, or in your bedroom or whatever, but you can't do engineering for a client. Suppose a client comes, well, can you design a house for me? You can't design a house and give it to him because it is against the law in many countries. You need to have something called charter. Charter, or in US it is professional engineer status, to sell your services, sell your engineering services to a third party. So initially everybody becomes an engineer to himself by doing little things at home. For that you don't need a license. But to practice it as a profession, sell the engineering service to others and charge money, you need to get either charter. In Europe you need to get the charter, in US you need to get the PE status. So likewise the career develops. Initially it is for yourself, then second for the third party, and you can earn a living out of it. So that's how to build a career. So if you have not built a single circuit at home or not experimented with the radio at home, you are not going to become an engineer. Radio engineer or electronic engineer. Some people want to become engineers by learning the theory. They will never do. They will be disappointed in certain amount of time, seeing that okay, a lot of other people become engineers and they perform very well. Why can't I? I have learned this much of engineering. But who cares? If you can't do anything, however much you have learned is useless. So nobody will care. This is the type of profession you are in. You are in a profession where practice makes you perfect. And it is good news for all of you, I know, because you all have the capability to practice it before learning it. In fact, we tried in the university, just to give you an example, sometime back we only had a final year project. After they go through 3 years, the 4th year we have an intensive project. And the quality we get out is very poor. Most of the time we find that, okay, it's brilliant in theory, but the gadget does not work. Maybe wiring is poor, they don't know how to connect, and so many mistakes. Once we observed that, we started introducing a level 1 project, which is called a June term project. I think you might already know that. June term project we started recently, and the idea of the June term is before you do theory, you do the project. First year you have completed barely small amount, but you are supposed to make a little gadget and make it work. And that helps a lot to improve final year project, the data we observe. So nowadays, in our department, we are practicing to introduce mini projects to every subject in level 2, level 3, because we have seen the improvement that came through that little project we introduced. It was only 7-week project, and that did a big change in the quality of the output of the final year. So that simple story tells you a lot of things, isn't it? Because first years don't know anything about the theory before they make the gadget. But they get the gadgets running. If you have visited the exhibitions, you would have seen little gadgets like that. One set of boys have made something called clap lamp, where you can touch from there to clap, it will switch on. So when I asked, why did you think like that, they said normally when we return home at night, we are groping for the light switch, right? And we enter at dark and collapse and everything. So this is better, you clap twice, it will come. Simple thing, and they have made it very perfect. And I asked, what is the cost? I want to buy. They wanted to give one free to me, but then I said, tell me the cost. They said, we will sell it at 800 rupees. And I got it, but later my vice chancellor dropped it from me, and he said, no, it's not for you, give it to me. So then I had to give it to Professor Vijayasekar. He is using it right now. But it is a very marketable project. Unfortunately, the students are not marketing to that level yet. But it's a marvelous piece of engineering, I thought. So it's very useful, effective. But gadget is very simple, very little circuit. Sound detector connected with the lamp switch. A lot of people might say, okay, what is this very simple level of electronics? But the usefulness is really great. In the garage you can use it. Whenever you find that the light should come on without you groping for the switch, it is very handy. It's a table lamp and very nicely made. And any one of you can make it, isn't it? You don't need to study power density or anything for this. So start doing it. Start doing it now, because it will keep on adding to your practice. So by the time you get all these city and guild qualifications, etc., you are already an engineer. Qualification is just an ornament to you. It is not a must. It is not a must. It is an ornament. People wear in order to go for interviews and all. But once you get selected, the company will pay you for your performance, not for the certificates you have. That's from my experience. I also went through this engineering degree first, but later on I started realizing you don't need a degree to become a very bright engineer, very good engineer. In fact, our previous vice chancellor told me that Ray Vijayawardene, he said he didn't go for any qualification, and he is one of the brilliant engineers I have met. He designed the tractor, the hand tractor, what they call it. He was a designer, and Japanese took the design and started making it. So likewise, what I am trying to say is, get the theory only when you want it. Go for the theory only when you want it. Till then, start practicing. Then you get held up due to something. Now start searching for the theory. That is the best way to learn. Right. We now realize that d upon lambda ratio is a very important thing. Okay? So if the lambda is small, even with a small diameter, I can get very high gain. So we'll measure that. Okay, Lord sir. Like that. Gain is proportional to d over lambda square. Proportional to this ratio square. Therefore, mouth diameter to wavelength ratio. Mouth diameter to wavelength ratio is very important to get high gain. From the dish antenna. Maybe you can remember these simple equations. Then gain is 70 times lambda over d over lambda square. That was Now, instead of efficiency and phi, you can combine them, and typical value is about 70. So, very simple equation to quickly calculate the gain of a disk. The beam width of the disk, 3 dB beam width is, sorry, I'm sorry, this is not 7, this is 6.1. It is 70 lambda over in the equation. These are simple equations you find in textbook. They are useful to find out what is the beam width of a disk, what is the gain of a disk. So when you have a disk, it has a beam line. Beam width is this half power gap. This is theta 3 dB. When 3 dB beam width is small, you get a very sharp beam of radiation from the disk. Small beam width means sharp radiation. You have seen the torch, isn't it? Some torch have wide angle, some torch sharp radiation like that. That's the beam width. And again, if you have d over lambda high, what does this mean? If d over lambda is high, gain is high. Look at this, d over lambda high means gain is high. What will happen to this if d over lambda is high? This is lambda over d. Opposite of d over lambda. So if d over lambda becomes high, lambda over d becomes low, beam width becomes low. What does that mean? Very sharp focus of energy. Low beam width means sharp focus beam will go. So higher the mouth diameter with respect to the wavelength, you get two information. One is you get high gain. Second is highly focused beam, so energy will not go into unnecessary direction. Okay. You can summarize this. If the mouth diameter is high, with respect to lambda, if the mouth diameter is high with respect to lambda, it improves the gain. And at the same time, focuses the beam to a sharp beam of radiation. Now you can understand why we don't make a big dish. We don't make a microwave dish for your radio. You have FM radio at home. And you might use FM radio. You might use a dipole kind of thing. Why don't we make a big dish and we connect it there? Then the gain might be good. Why not? And then can connect a big dish and collect energy. Problem is, how big should I make in order to get the same gain as a dipole? Dipole is 1.64 times high. Then but if you gain is now it's about 6.5 times d over lambda square. Even to get a gain of 6.5, what should be my d? Just suppose I want a gain of 6.5. What should be the diameter? D over lambda should be 1, isn't it? But if this is also lambda, it will be 1. Then I get gain of 6.5. And what will be the D then? D equals lambda means for FM. For FM, what is the lambda? Take something like 100 megahertz FM that you listen. Just use T equals F lambda and find the wavelength. You are listening to that at home anyway, so better to know the wavelength, isn't it? What is the channel on 100 megahertz? There is somebody transmitting at 100 megahertz.
3 meters.
It can be millimeters.
No, 3 meters.
3 meters. 3 meters. So that was the problem. Now you can see. If you want that kind of even little gain like 6.5, you need a 3 meter diameter antenna, which is a big one. 3 meter diameter will be half the roof. Okay? Big one, and the volume, weight will be very high. And not nice to connect that kind of unproportionate thing to your radio, isn't it? So that is the risk. That is the risk. But at the same time, the microwave dish has become very popular in your toy. Why? Lambda is small, so with few centimeters in the mouth diameter, it's a very sharp wave. So it is not diameter what matters, D over lambda ratio. D over lambda ratio. If the lambda is big, you need the big diameter to make the ratio high, and it becomes impractical. Not practical to make it. Or impossible sometimes, because diameter could be 50 meters or something. Sometimes impossible. Sometimes even if it is possible, it's not with the correct weight or the size. But the theory is uniform. Theory is applicable to any frequency. It is a uniform theory. Problem is the wavelength you receive. And any examples where you know the this kind of dishes being used to receive very low frequencies? According to this theory, when frequency is very low, lambda is large, isn't it? When the lambda is large, D over lambda is difficult to get high. But people have still done that. There are antennas made from the ground. In some other countries here, but what they do is, suppose this is a mountain, they may cut this portion of the mountain, make it a parabolic cut, and concrete it like that. You concrete it like this. On top of the concrete, you put aluminium foil. Like that. And that is a nice dish antenna. And then you can have your receiving point here. Then sky signals are received here. And this could be sometimes 100 meter long or 500 meter long. Very big antennas are there. For what? For listening to sounds coming from outer space. This is called space probe antenna. And those are very low frequencies. Coming from distant stars are very low frequencies, like 10 kilo, 15 kilo hertz. Those are the frequencies. And to receive them, you need very big dish antennas. Otherwise, you can't hear those faint sounds coming from distant stars. And nobody knows why those sounds come, but they come. They keep coming because that is due to various movements of stars, collisions of stars, etc. And some astronomers, it is in astronomy, they keep looking at or listening to those sounds. And so this is an example where dish shape has been used even for very low frequency, like 10 kilo. This is a very big one because you can't hold it up. You don't manufacture it in metal, you manufacture it in concrete on the ground. Then nobody is holding it up the ground. So those are different engineering ideas of how this theory we learn can be put into practice. So just when you work out, we are going to stop. Just when you work out, have a look at that tower. You'll find 3 different sizes of dish antenna. Just observe them and go. If you can just tell which antenna is of which frequency, you are a very good engineer on that area. If you cannot today, don't worry. We will define it later. But just observe today, there are 3 different kinds of dish antennas on top of that tower, right? That's the point we are going to stop. So just look at the top of the ADJ before you go. Okay, thank you very much. Next time we will be having our class in the usual side, the other side of the